Exercise 2.5. Sketch the rational function y equals 3x minus 2 times x minus 4 divided by x minus 1 times x plus 4. Okay, so first we gotta collect our information like usual. Just to make some of this a bit easier, let's expand it out as well. So that will be 3x squared minus 2x minus 12x, so minus 14x, and then plus 8, divided by x squared, and then minus x plus 4x, so plus 3x minus 4. Okay, so we immediately know that there's a horizontal asymptote, that is y equals 3. We can see from the non-expanded form, the linear factor form, that we have two vertical asymptotes, x equals 1 and x equals negative 4. We can find our x-intercepts very quickly. X-intercept, this is when y equals 0, and y can only equal 0 if the numerator equals 0. So that would be x equals 2 over 3, or x equals 4. And our y-intercept is when x equals 0. So the y-intercept is 8 over negative 4, so negative 2. And we saw when we did the last exercise that this thing will intercept with its asymptote as long as this number times this number minus this number times this number doesn't equal 0. At least I think that's what it was. And I can't remember what it ended up equaling, so let's just derive it again, because that's pretty easy. So we just set this thing equal to negative 2. So let's suppose it equals negative 2. Its horizontal asymptote, and then that's true if and only if 3x squared minus 14x plus 8 is equal to negative 2x squared minus 6x plus 8. Okay, so the 8's cancel, and then we get 5x squared minus 8x equals 0. So of course we can factor out x, and then 5x minus 8 equals 0. So it intercepts its asymptotes when x is equal to 0 or x is equal to, sorry, not 5 over 8. If I said 5 over 8, I was thinking 5 over 8, 8 over 5. So 1.6. We can also find whether it has maximums or minimums, or none, by differentiating the equation and setting it equal to 0. So dy over dx is equal to, so 6x minus 14 times x squared plus 3x minus 4 minus, and then the derivative of the bottom one, so 2x plus 3 times 3x squared minus 14x plus 8, and then the whole thing divided by the bottom one squared, so that is x minus 1 squared times x plus 4 squared. And since we're looking for maximums or minimums, we set it equal to 0. And so we just have to deal with this top part now. So, okay, let's expand it out. So 6x cubed, and I'll just pause the video and do it myself. Alright, I'm sure that was preferable to watching me mumble my way through that. But I'm going to make you watch me mumble my way through the next part, where we just simplify everything down. We have 18x squared minus... no, I'm not going to make you watch this. This is just too boring. Okay, so simplifying everything down, we end up at this quadratic equation, and you can check that delta is less than 0, so there are no real roots, which means there are no maximums or minimums of this function. Just to sidetrack for a few seconds, and we'll return to this at the end. Given all the work we just did calculating y prime of x for the previous function, an interesting question that you might want to work on is if we have y equals ax squared plus bx plus c divided by x squared plus dx plus e, can y prime of x equal 0 for some x as a real number? So is it possible to actually have the derivative equal to 0 and therefore maybe some maximums or minimums? By the way, or points of inflection. By the way, it doesn't matter whether there's a number here or not, because a, b, c, d, and e are just arbitrary real numbers. So we can divide the top and the bottom of this fraction by f and still have arbitrary real numbers here. So I'm just gonna leave it in this form, because I think it makes the working a little bit easier. So yeah, something to have a play with, and we'll come back to that at the end. And finally, before we sketch this thing, I guess the last thing we can do is calculate the range of this function. So let's go ahead and do that. We can do this using the same technique as usual. Just find all of the values of y for which there are at least one value of x that can be sent to them. So we have y minus 3, lots of x squared, and we have 3y plus 14, lots of x, and then as a constant we have minus 4y minus 8. So minus 4y plus 8 constants, and that should equal 0 if x and y are a pair that solve this equation. And then we just check where the discriminant is greater than or equal to 0. So 3y plus 14 squared minus 4, well, it's going to be plus because there's a negative over here. So plus 4 times y minus 3 times 4y plus 8. And we need that to be greater than or equal to 0. Okay, and there's the kind of boring expansion that you didn't have to sit through. And we can see that this is true for all values of y. True for all y, since 25y squared plus 68y plus 100 equals 0 has no real roots. So therefore the range is all real numbers. Okay, just compiling all the useful information here and making an x and y axes, I believe we are ready to sketch this rational function. So first up, let's draw in the asymptotes. We got an asymptote at y equals 3. So sketch that. So you should always draw your asymptotes as dotted lines. And then write y equals 3. And then for the vertical asymptotes, we have one at x equals 1. Excuse my terrible scale. When you do it on paper with a ruler, I think it should look better. So x equals 1 and x equals negative 4. So about here. So x equals negative 4. Alright, what else do we know about this thing? we know that it has x-intercepts at 2/3 and 4. So 2/3 is here, and then 4 is about here. So those are our two x-intercepts. And we also know that it intercepts its asymptote, and I probably should have wrote horizontal asymptote. Horizontal asymptote when x is equal to 0 or x is equal to 1.6. So we know it goes through this point here. When x equals 0, it goes through the horizontal asymptote, y equals 3. And when x equals 1.6, so it also goes through this point here. And just looking at this thing now, I can tell I've made a mistake somewhere, because as x tends to infinity, it should get closer and closer to the line y equals 3. But we can't have a point here and a point here, because then otherwise it would need to look like this. It would need to come down, and then it would need to curve around again somewhere. And it can't curve around because there's no maximum or minimum. So either I've made a mistake here or I've made a mistake here. So let's go back and check the working. Alright, so horizontal asymptote y equals 3, y-intercept y equals -2. And then I see that when I was checking to see whether it intercepts its asymptotes, its horizontal asymptote, I accidentally set the function equal to -2. My bad. So if you were sitting there shaking your fist at that point, I do apologize. Yeah, sorry, my mistake. And I really should have caught that in my working, because if I was practiced enough, I should have known that there wouldn't be a x squared term in this equation, because if the asymptote is y equals a divided by b, then just by construction the x squared terms are going to cancel out anyway. So terrible mistake on my part. Let's go ahead and do that working again. Alright, so let's replace it with 3 this time, and then when we do our expansion, we're going to get 3x squared plus, minus 14x plus 8. This should be equal to 3x squared plus 9x minus 12, and then the 3x squareds cancel as they should, and we are left with 23x equals 20, and so x equals 20 divided by 23, which looks much more realistic. So intercepts, so our function r of x intercepts the horizontal asymptote y equals 3 when x equals 20 over 23 and no other value. So let's go down and correct that. So intercepts its horizontal asymptote when x is equal to 20 over 23. So that is bigger than x equals 2/3, so it's going to be here. And that makes a lot more sense, since it should be getting closer and closer to the vertical asymptote at that point. Okay, moving along, we also have a y-intercept when y equals -2. So that should be about there. And what else do we have? I think that pretty much covers everything. And I guess we should go ahead and label all those points. So 4, 2 over 3. And then this one is, this point here is 20 over 23 and 3. And then the y-intercept was -2. And then yeah, other than that, we're good to go. Let's sketch this graph. So it's going to look like this. Well, it has to look like this because it's well, it's gonna go upwards, and we know it goes through this point, and this point. So it's forced to go upwards because it can't turn around anymore. It can't turn around because there are no maximums or minimums. So it looks like this. And then again, since we can draw it without taking our pen off the page inside here, it has to take this kind of shape. It has to go downwards. It cannot turn around and go upwards because there's no more x-intercepts, and also there's no minimums. So it's forced to take this shape as it comes down here. And you can also check that as x goes towards -4, the function becomes extremely negative. Now on this side over here, it goes through the point x equals 4, y equals 0, and so it cannot do this. Because then it would need to curve around again, because it needs to tend towards y equals 3, as x tends towards infinity. So and because it can't curve around anywhere, the only thing it can look like is this. It can't look like anything else. So that's all it can really do while meeting all the conditions that we figured out over here. And then similarly for the last one, there are no x-intercepts, it can't curve around anywhere, it has to tend towards y equals 3 as x tends towards -infinity, so it has to look like this. There's no other possibilities. Okay, so that's how to go about sketching these things. Please be careful with your working, don't be like me and make silly mistakes, or if you do, then be like me and catch the mistake before you hand in your exam paper.